So it's my pleasure to introduce Dr. Anatoly Miroshnichenko. Dr. Miroshnichenko got a PhD from Pulkovo Observatory, then went on to postdoc at the University of Toledo in Ohio, and is currently a professor at the University of North Carolina at Greensboro, where he's been since 2005. We're lucky to have him talk to us today about BE stars and B bracket E stars. So please, Dr. Miroshnichenko, take it away.
Okay, thank you. Hope you can hear me all right. So first of all, wish you a good time of the day. First of all, let me thank the organizers for inviting me here. As a matter of fact, in the beginning, I misunderstood the information about the audience. I thought it was some kind of a more local seminar, but then I read the announcement better and looked at the webpage of the IAU working group on active B stars and found that I know many people there, read their papers and familiar with their results. So for some of you, my results may not be very new, but some of them are pretty recent, published this year. So in any case, I can be excused about my not very good attention, as my friend Jelka Ivisic, who is now director of the Vera Rubin Observatory, said, answering a question about my age about 30 years ago, he said, he is ancient. So, and that antiquity brings me to a little history of my research interests since the very beginning of my career. I started in the early 1980s, and my master thesis was devoted to a search for galactic supernovae, which, you know, we've been missing since Kepler's time. And at that time, it was considered a joke because robotic surveys were just in the beginning, not very well known, but now they are pretty routine. Anyway, when I got my first job at the Pulkovo Observatory in St. Petersburg, Russia, I switched to young stars, mainly Herbig AB stars. And in an attempt to enlarge that group, we turned to a list of B-brackety stars, which were discovered about a decade before that time, started observing them, first photometrically, then spectroscopically, learned that they are not mostly young stars. And so this became the main topic of my research since that time. Then when I came to the University of Toledo to work with Karen and John Bjorkman, I switched also, not switched, but expanded my interest to classical V stars. And this is what I'm going to talk about today. Let me share my screen. Okay, this is going to be here. Share. And then, is it in the presentation mode or not?
Not yet in presentation mode, but we can.
Okay, so let me. Yeah, is it now?
It is, yes.
All right. So a little bit about my affiliations. My main place of work is the University of North Carolina, Greensboro. And I also affiliated with the Fesenkov Astrophysical Institute and Al-Farabi Kazakh National University in Almaty, Kazakhstan, where I still work with colleagues because I was visiting that institution in and out since the very beginning of my career. And I also share my experience with graduate students. So several of them have already defended their PhD thesis. And in recent papers of our group, you can see them as first authors. So in the first slide, you see pieces of the sky map with two objects. One is the first B star found through visual spectroscopy in the middle of the 19th century. And second is the brightest object with the B-brackety phenomenon, which was also found as an emission-line star in the 19th century, maybe early 20th century, but their real nature was revealed only in the beginning of the 21st century. Turned out that they both are binary systems, and it took lots of observations and different kinds of analysis in order to figure that out. Let me see. So I can advance my presentation. Okay, so I'm on slide 2. It was a little slow. So here is an outline of my talk. A brief presentation of the basics of radiative transfer in stellar atmospheres and circumstellar medium. Then some parts about differences between the evolution of single stars and interacting binary systems, because turns out that objects from both groups, B and B Bracketed, probably had a part of the evolution exchanging material. Then they'll introduce the different kinds of binary hypothesis, because it was different at different times for both groups, and show some results of studies of objects with both phenomena, which me in my group, some of the collaborators are listed at the bottom of this slide, but there are more of them came up with during probably the last decade. All right, so what do we observe from stars? You know that the star is typically an intransparent object with lots of material, and continuous spectrum comes out of the photosphere. But on the way out to space, it encounters interaction with the transparent layer of the star, which we call the atmosphere. And then some photons which were intended to end up in our eye or the telescope get absorbed by some atoms of the atmosphere and then re-emitted, but not necessarily in our direction. So we observe a deficit of photons at certain wavelengths whose energies correspond to the energy level structure of the atoms present in the atmosphere, and we observe an absorption line spectrum. So these are normal stars, and the spectra depend on 4 main parameters: surface or effective temperature, surface gravity, then rotational speed, which is projected rotational velocity, since the axis of rotation is randomly oriented with respect to the line of sight, and finally the chemical composition of the atmosphere. Then every star has some circumstellar medium, but if the number of atoms in the circumstellar medium is pretty low, then we don't see the consequences of the processes which happen in the circumstellar area. And what is happening is that when a photon gets out of the atmosphere, it can be intercepted. It can first ionize some of the atoms which are located in the immediate vicinity of the star, and these photons should have pretty high energies, mostly ultraviolet photons. Electrons get free, but pretty quickly they get captured by other atoms of the circumstellar material. And then at the capture, a photon of random energy is emitted, adding to the observed continuum from the star. And then when it goes down, energy levels, radiation in spectral lines, but now it's an additional radiation, it's emission lines, gets into the spectrum. And if the amount of the circumstellar material is low, then we don't see these effects. But if it's relatively large, then emission lines and more continuum appears in the observed spectrum, and we start seeing these effects, and that's what we see in B stars and B Bragg stars. So depending on the distribution of the circumstellar material, we see different kinds of emission line spectra. So at the bottom of this slide, what is going on in a typical stellar wind is shown. the photon is absorbed in the region which faces the observer, the the distribution of optical depth is different there, and we see an absorption part of the spectral line, which is shown on the left at the very bottom. And then from everywhere else, due to scattering of newly created photons in the circumstellar medium, we see an emission part. And the combination of the two gives us a well-known P Cygni type profile. But that's the accelerated stellar wind. If the distribution is less homogeneous in terms of its geometry, it's not very spherical, it's kind of a disc-like, then we're going to be observing typically a double peak profile, but it also depends on the orientation of the star's rotational axis, and as a consequence of the disk plane towards us, and the appearance of the profile depends on how the Doppler effect works there. If the disk is face on, then or most of the motion occurs in the perpendicular plane to the line of sight, and we don't see the split in the profile. When we change the tilt of the circumstellar disk, then we see separating peaks. The blue shifted, which is formed in the part of the disk which moves towards us, and the red shifted peak, which forms in the part of the disk which moves away from us, separated by what is called central depression. It's not an absorption feature. It's simply deficit of radiation, because the part of the disk which is projected onto the line of sight has a smaller amount of material. And then when we change the tilt of the disk to an extreme, almost edge on, then this part of the disk which gives us the central depression is so small that the central depression goes underneath the continuum. So that's what is happening in the stars, which first were discovered by visual spectroscopy in the middle of 1860s. And since that time, it took about a few decades to actually put together a number of stars and define a class of V stars. At that time, beginning of the 20th century, and many other objects were considered members of this group, and now we know that some of them are supergiants with mostly stellar winds. Some of them also have dusty envelopes or extensions of the circumstellar disks, which are known as objects with the Vibrakity phenomenon. And the B star group or the B phenomenon separated from that bulk of the emission line stars. And the main features of the E stars is that the circumstellar gas is located in a disk. The star itself rotates very fast, which actually changes the even the effective temperature across the surface of the star. And the luminosity of most of those B-type stars is close to the main sequence, not necessarily at the zero-age main sequence. There is definitely a distribution, but they're not very far from the main sequence. They are mostly B-type stars with a few O stars and a few A-type stars showing same kind of features. There was a long-term debate about how these stars formed. First of all, why they rotate rapidly. There are two possibilities, two main possibilities. Maybe intrinsic fast rotation rate, which may have come from the initially faster rotating interstellar cloud, or it's an induced fast rotation from a mass transfer in the binary system. So it looks like the second possibility is prevalent. information of V stars. And then we need to explain the disk formation. And it turns out that it came from the mass loss from the B-type star. It's called decretion disks, opposed to accretion disks in premium sequence Herbig V stars. And it turns out to be triggered by non-radial pulsations. So there's a picture on the left showing effects of non-radial pulsations with different colored zones to have different distance from the center of the star. And it was confirmed by photometry from small space telescopes, which shows that regular brightness variations of different time scales and very low amplitudes, a few millimagnitudes are observed in those bright D stars. And then when the material is out of the B-type star, it moves outwards by viscous energy transfer, but it depends on the speed of that material. If it's not enough, then it may fall back onto the star, or if it's too high, then that material can go away from the star or get accumulated in the disk. And it turns out that most B stars form their disks and then lose them different time scales from probably several months to several decades. And until the beginning of the 20th century, when massive spectroscopic observations began, not many B stars were known as binaries, but now we know that among at least the brightest and hence most observed B stars, about, I believe, close to half of them were proven to be binaries. And I will show some of those proofs in the next part of my talk. So what kind of binary signatures we can observe? Obviously, if the components of the binary system have comparable brightness, then you can see two systems of spectral lines which move in the opposite direction. Again, depending on the tilt of the rotational axis of the system. If we see them, the axis pole on, that it will be hard to detect that motion. Then we can observe periodic radial velocity variations of the spectral lines, and that's what we are looking for in proving binarity of B stars, similarly to finding exoplanets. Also, you can observe different positions of the continuum and spectral lines on the image on the detector. This method is called spectrostrometry. It was actively used by some of our colleagues in the late 90s and early 2000s, but I don't see much kind of development of it and new results. And it's interesting that there are some B stars, B Brigade stars, which are shown to be binary through spectrostrometry. This result was not confirmed by other methods of observations, and especially the spectroscopic method. And then, of course, you can detect secondary components directly by imaging or interferometry. But in this case, the systems have to be pretty close to us. Otherwise, we cannot resolve the components. So why is it so difficult to detect binaries in B star systems? Same for B Brigade stars. First of all, fast rotation, which makes the spectral lines broad. I will show you an example in one of the next slides. Because of that, first of all, these are B-type stars, and they don't have many spectral lines in the spectrum, many noticeable deep spectral lines. When they're broad, then some of not very deep lines blend with the continuum, of course, depending on the signal-to-noise ratio. And we have less number of lines to study, that either cross-correlation or just measurements of individual positions of spectral lines. Then, second difficulty is that the secondary components are typically much fainter in B stars. You see the difference in the V-band brightness. They can be even 5, 6 magnitudes fainter, but spectroscopic methods can actually discover those, provided we have a good coverage of the behavior of the stars. And then absorption lines, although they are mostly present in these stars, they are distorted by the circumstellar material. Some emission lines fill in the absorption lines. For example, in early B-type B stars, hydrogen lines are almost fully in emission. Then some of the lines, for example, iron 2 lines may blend with absorption parts, and with helium lines can be in emission, and it makes the number of lines to study to discover binarity even smaller. Also, the effects of the binary evolution, especially mass transfer, may be felt when the mass transfer episode is already over. Here you see a Hermann-Russell diagram with evolutionary tracks of single stars. Those black lines, and an example of evolution of two components of a binary system with initial masses of 7 and 6.3 solar masses. When the more massive star leaves the main sequence, it feels its Roche lobe, starts losing mass. The lower mass companion accelerates its evolution and moves along the blue track, but the former more massive companion loses mass and luminosity and moves down the diagram towards cool stars, and then it rebounds, recovers. But the final mass here, if you just observe, for example, this star, is very different from what you would invoke from the evolution of a single star. So we really need to restore or somehow learn about the history of the evolution of those stars. And here is the effect of projected rotational velocity. I showed a comparison of two spectra, one a B star 60 sig, and the other one is a normal star, gamma peg, which have very different projected rotational velocity. 30 over 300 kilometers a second, and you can definitely see that some of the lines in the spectrum of gamma peg, they have pretty similar temperatures, over 20,000 degrees. So you can see many spectral lines, even at this not very high resolution. These spectra were taken with Telescope of Power Observatory, which will be introduced a little later. Some of those lines which you can resolve in a non-high rotating star, they get blended and they get broadened, and basically they go into the noise. And even the very strong lines, they become weaker and they become broader. So it's really hard to study the variations of the radial velocity in this, for example, B star, also because the secondary companion has a much lower mass, and it produces not a very strong gravitational effect on the main component of this system. Okay, so what we get studying the binaries, we derive orbital periods and then get spectroscopic masses, companion separations, and from that sizes of the disks. Turns out that they're not very large, and as a result, they don't have very cool areas in the outer parts of them where dust can form. So B stars do not have dusty parts of the disks, or if there are molecules in the outer parts, they don't produce a noticeable effect in the observed parameters. So the main disk is responsible for the light emission and excess of radiation, not only in the infrared region, but also in the optical region, which is pretty small, but may need to be taken into account in order to derive the true luminosity of the B star. Then the secondary may also have some circumstellar matter, and I will show you one example of such a situation. Then we now limited to two main spectroscopic methods to find binaries, which were reviewed before, but with all these features of these stars, we can rely on periodic radial velocity variations and pretty recently emerging new method of searching for periodic intensity ratio of the double-peaked line profiles, which may be phase-locked with the orbital period. Of course, there is also a method of ultraviolet spectroscopy when you see the contribution of the secondary companion in the ultraviolet, but unfortunately, we don't have an ongoing mission which would extend, which would allow us to use that method on more stars. Now, a caveat here, the phase-locked variations of the peak intensity ratios, mostly in the H-alpha line, but other lines can be used as well, which are known as V over R variations. They typically occur in weak line B stars. In strong line B stars, those variations may have much longer periods. Again, I will show one example, but maybe they show both periods, the orbital period and something much larger. So the main method until recently, so using not absorption lines, but emission lines, was NERD line profile method. So this is an example of an H-alpha line. I don't remember what the star is, maybe Kappa Draconis. So you plot or somehow use a code on a emission line, H-alpha emission line, which is observed in the heliocentric rest frame, converted into radial velocity space, and then inverted along the radial velocity axis. It makes you the red profile, and then you shift the red profile back to the to match the wings of the line, and half of that shift gives you the radial velocity of the emission line. So it's a good method, but it works best on large shifts, large amplitudes of the radial velocity changes. Then it's a little bit limited because some observatories are located in pretty wet places, and there are many absorption lines due to the Earth's atmosphere, telluric lines, which need to be cleaned somehow. And different methods of cleaning have been used, but in any case, it works. But for this method, again, to work best, the line should be pretty symmetric. In a number of cases, it's not symmetric in terms of its intensity in the velocity space. And it's really hard to figure out which part of the emission line profile is to use properly to determine the radial velocity. And also, we don't know whether it's a this radial velocity traces the motion of the star, because it's a circumstellar material which moves at some maybe different radial velocities around the star. So this method was successfully used on the first discovered B star, Gamma Cas. It was done about 20 years ago. First, Peter Harmanetz used medium resolution observations from the Andreev Observatory, came up with the orbital period of 23.6 days and an eccentricity, pretty noticeable eccentricity. At that time, our team at Toledo was observing the system, and you can see the radial velocity variations on the lower part of the picture. You see that in the left part of this picture, which represents late 80s, early 90s, actually to late 90s time period, the observations were not very frequent. And that's why it was impossible to figure out that it was a binary. But since about the year 1996, observations became more frequent. And here you can see definitely a regular pattern. So our data alone showed about the same period, but zero eccentricity, so circular orbit. Then about 10 years later, our teams joined our data, and the final orbit turned out to be circular. That was our result, but the period was much closer to the Peters result. Anyway, now we know that gamma CAS is a binary system, and it's actually good to keep observing it, which we are doing now at our observatory. So most of the next results, which I'm going to report here, have been obtained at the Free College Observatory, which belongs to basically our university, because only our research group uses it for observations. We have in the shell spectrograph from a Chiliac company in France, which was originally manufactured for amateurs, but it's a very good instrument. It allows to have a spectral resolution which is capable of detecting radial velocity variations down to about a few kilometers a second. The accuracy of radial velocity is about 300 meters per second. We can observe almost the entire optical range, and we started doing that in late 2011. By now, there have been about 1,200 nights of observations, and we have taken about 10,000 spectra, which are soon going to be released to the community. We just need to complete transition between storage spaces, which is done by our university. So this is our telescope, 81 centimeter telescope, which was automated completely in 2019. So we can actually observe from anywhere in the world where internet connection is very good. Now, let me start reviewing our recent results. First, it's a bright star. All of them are going to be bright stars, mostly naked eye stars. New Geminorum in constellation of Gemini, the twins. It is known for its double peak profiles with changing V/R ratio. But at some points of time, this profile was even more complicated. It was noted in a paper by Thomas Redinius in, I think it was 2006. They noticed some triple peak profiles. But in the archive of the Ritter Observatory of the University of Toledo, I found some profiles which had even 4 peaks, that red profile on the right. So in that paper by Thomas, which is referred here on the left, they tried to find the binarity of the B star in this system, which was known as a binary or triple system. Actually, even more components have been reported in that system, up to 8 components found by lunar occultations. But we are now talking about a triple system. And it turns out that in the 90s and early 2000s, the V/R ratio in the alpha line profile was behaving pretty weirdly. And a reflection of that, those strange triple and quadruple peak profiles. And the ratio was all over the place. So the blue dots and green dots are the results reported in Thomas' paper. You see that you cannot actually figure out that there was any regular variations in the V/R variation of the H alpha line profile. But since that time, that ratio mostly settled down. The magenta points show the mostly amateur observer spectra from the best database, and the black ones are our data. And if you remove the trend, then you will see that you can actually nail down periodical variations. But even recently, Robert Clement and the team ended up with the conclusion that the VE star is the tertiary component of this system, because no periodic variation have been discovered in the VE star behavior. It turns out that it was not really correct. When we did our study, after taking about 200 spectra over 10 years, we did cross-correlation of a part of the spectrum, because fortunately, New Geminorum has not a very large projected radial velocity. So this is on the bottom right, you see an average line profile with pretty many lines. In the cross-correlation results are shown at the bottom left. So it's a pretty convincing radial velocity curve. Periodic curve folded with the orbital period, which was reported earlier. We just refined it a little bit. It's about 2 months, 53 days. But the same behavior show the V over R variations in the H alpha line. And the conclusion is that the VE star is not the third companion of the system, but the second primary companion. So it's one of those stars. And no wonder that astrometric study of this system was not reconciled with the previous results for the masses and the locations of the companions. So that's a pretty interesting result from our studies, which was recently published in the journal Galaxies, and special issues on binary stars. Second example is another bright B star, Pi Aquarii, which was done at the University of Toledo. That was our previous discovery of binarity. So you can see that at different times, the star got different visual brightness. There is no time scale on the left, but the part of time shown here starts in 1950s and ends around about 2000. In the 1980s, the disk was very strong. H alpha emission was very large. It is shown in the next slide. And the star was brighter by about 40% compared to the end of 90s, when it totally lost the disk. And you can see that during the diskless phase, the spectral energy distribution, which was combined from the optical photometry and IUE ultraviolet spectrum, it matches a model which is shown by the line here. So there is no difference between the theoretical model for a naked star and the observations. And during the active phase, back in the 1980s, the optical and infrared excess is obvious. And in the ultraviolet, it's the opposite. Of course, no difference in the between the model and the observations when there was no disk. And the spectral energy distribution, the spectrum in the ultraviolet was weaker compared to the model, because some of the radiation was captured by the circumstellar material and got transformed into the infrared excess in optical. So when the star lost the disk, the only emission feature which was left in the H alpha profile was that little emission component, which was found to be moving within the absorption line profile from the atmosphere of the V-type star. And on the left, the squares show the radial velocity of this little component folded with the orbital period of 84 days. But at the same time, the rings of the H-alpha line were also moving in anti-phase, and the open squares show its radial velocity, velocity curve followed with the same period. So it was obvious that it was a binary, but if you remove the spectrum of the bright star, of the B-type star, then you can figure out what the emission line would look like in the spectrum of the secondary component, which is much fainter, about 3 to 4 magnitudes fainter, and it is shown in the lower right picture. So this material was left around the secondary companion, and the primary component has lost the majority of its disk. Then in the 2000s, the disk around the B-type star reappeared, started showing phase-locked radial velocity variation. This is the upper picture on the left. We studied it with the Doppler tomography method and restored a density structure of the disk, which showed that there is some density enhancement shown in the red color, which moves in sync with the secondary companion. And here, what we see, what kind of a H-alpha profile was observed at the top of the disk phase back in the 80s, and when the star was losing the material. So in the 1990s, it's a classical double peak profile, but in the 1980s, it's sort of a single or triple peak profile. But when you see such a profile, which is, by the way, observed in gamma CAS as well, it's not necessarily due to the tilt of the disk. It just may be a central component which masks or veils the double peak structure. So this, I think, modeling of such profiles need to be advanced in the next years. So next one is Kappa Draconis. Kappa Draconis is very similar to Nu Geminorum. It has a similar temperature, surface temperature of the B-type star, about 14,000 degrees Kelvin. It has a little bit larger rotational velocity, and we used the same part of the spectrum to do cross correlation, which resulted in radial velocity variation shown on the top panel of the right-hand side picture. Then the V over R, if you plot them just versus time, it's really hard to make conclusions about the regular variations, but you do Fourier analysis, and it shows exactly the same period of about 62 days. And you can see that the V over R variations are phase locked, and they also go in sync with the motion of the secondary companion. Now, Kappa Draconis was also recently studied with astrometry and with more spectroscopy. It was shown in another paper of Robert Clement and the team that the star was losing its circumstellar disk. And on the left, I show here results of very recent study of our team led by Ilfa Gabridova from Kazakhstan. So in 2014, the line was strong, and with time, the emission line profile was getting lower and lower. Now it's totally out. There's just a little companion similar to that small companion emission component of the line in Pi Aquarii. But we did Doppler tomography of this star, and here is the structure of the disk. Its velocity space. The plus shows the position of the main component. Another plus is the secondary companion, and this is the disk which surrounds the primary companion. And in the red and the black, the largest density is shown, and this density enhancement moves with the disk in sync with the secondary companion. We now, I think, have more data to study more stars with Doppler tomography, which would reveal us more features of the structures of the disks in B-type stars. Another object is Beta Canis Minoris. It's a even brighter B star with very controversial results on its binarity. About 7 years ago, using our and amateurs results, we came up with a period of 183 days, which is very suspicious because it's close to half a year. But it was sort of confirmed by a team from the University of Toledo who used a different set of spectra, partially overlapped. They got a little different results for binarity, 170 days, which was then questioned by Peter Harman's team. Those two studies, Delaunay and Harman's, they used the H-alpha line profile, the position of the H-alpha, the mirrored method, mirrored profile method. And Peter concluded that these changes of the position of the line probably come from pulsation. But our enlarged collection of spectra showed that this period of half a year is not going away. And it's not an alias, it's not in the spectral window. So we can observe this star more than half a year each year. So we consider that period real. The variations of the V over R ratio is very small, about 8%, but it's a pretty convincing phase curve. And just continue studying that star. And perhaps we can find confirmation of binarity from some other methods. Then a few other results which show a power of the V over R phase locked variation method. This one was discovered, the binarity was discovered from the ultraviolet spectrum by Wang and the company, and then Clement and his team confirmed that, refined the period to this value, showed the title. We did V over R variation study. This phase curve is pretty noisy, but the dominant peak in the Fourier spectrum is at about the same period. So now we keep observing that one in order to refine this result. So it works. Similar was done for Epsilon Capricorni. The period was determined back in the 90s. Then Revinius team improved it. We refined it a little bit with cross correlation of absorption lines and with the central components of Balmer lines, which do not move similarly. So central components, absorption course or central depressions of Balmer lines sometimes, or in more cases, do not follow the orbital period. But in this star, in this system, they do. And you can see that all kinds of methods show about the same results for the period of about 129 days. 66 was also known as a binary with a hot subdwarf O-type component. We did a V over R study, and it perfectly fits the period. We had only about 30 spectra. Now we have 60 and continue studying this one. But this method works here, and phase-locked V over R variations were not known for that star previously. This is the last example from the stars, which shows a stronger and more edge on disk of well-known the binary 48 Libri. If you plot the V over R variation over time, you can see that there is sort of a hint for the periodical variations, but the period is about 15 years or so. And the spectrum, when you look at it, it reminds a B-type supergiant, not a B star. Now, I think, I don't know, I'm over time, and I still would like to introduce a few results from our studies of B-bracketed stars. Should we do that next time, or can I talk for about 10 more minutes?
Just a couple.
Okay, sorry about that. That's my problem, talking too much in the beginning. So here is summary. I just don't read it. I believe that B stars deserve very good attention in the future. More spectra with a higher frequency need to be taken. And I believe it will reveal more binaries. I'm not sure that all B stars are binaries because some hotter stars may actually expel enough material from their surfaces to form some kind of disks. But these B stars should not have very strong emission lines. And all the strong emission line B stars, I believe, are binaries or maybe triple systems, as a recent study by René Oudmayer and his team suggests. All right, a few results about B Bracketed phenomenon. They're similar to B stars, but the main stars are not rotating that fast compared to B stars. This is a heterogeneous group. The main features are larger disks, which include some outer parts where dust can form. It means that the temperatures there are lower than about 1500 or 2000 degrees Kelvin, and there is enough material to show up as a strong infrared excess, much stronger than we find in classical B stars. About 30, 25 years ago, it was shown that this phenomenon can be shown by at least 5 different groups of stars. You see them here in the middle. And we were not happy with that fact that half of this initially selected 65 V-type stars with this phenomenon were classified, started looking deeper into them, and introduced a new group called FS Canis Majoris objects, which, according to our idea, our working hypothesis, are probably interacting binaries, not necessarily at the moment. Why? So first of all, they have a much stronger emission line profiles, much stronger than in B stars and supergiants with more powerful stellar winds. And in order to explain this line profiles, you need much higher mass loss rates, which are not supported by theory of evolution of single stars. Then, in addition to that, these stars have forbidden lines. That's where the brackets around E are in the name of the stars. Then the hottest show strong calcium lines, Paschen lines, and there are some other signatures of secondary companions, which are lithium lines and calcium lines in the spectrum of some of them, which mean that the brightness ratio of the secondaries to primaries is not that extreme as in B stars, but in many of those, it's a pretty large one. First recent result, the brightest star, third Puppis, which was shown in the first slide of my presentation. It is actually classified as supergiant, and you can see that by, for example, the strong silicon lines and oxygen lines, which are luminosity dependent. But cross-correlation of about 100 spectra taken at our observatory and a few at other observatories showed that it demonstrates a regular periodic behavior. The orbital period was suspected about 70 years ago, but the amplitude of the radial velocities was just derived in our study, and it allowed us, with the help of Danny van Beveren, expert in binary evolution, to restore the evolutionary history of this system. So it started as a 6 plus 3.6 solar mass binary. Then the higher mass companion filled its Roche lobe, transferred most of its mass onto the secondary companion. The secondary became much more massive, and it is that supergiant here, close to the end of its evolution. And the primary former, more massive star is now about 1 solar mass star, which can only be observed in the ultraviolet, and this is our modeling of the spectral energy distribution, which shows that the contribution of the secondary companion can only be revealed at wavelengths less than about 1,000 angstroms, which have not been observed. And by the way, in this star, we also see phase-locked variations of the V over R peaks in the alpha line profile, but from cycle to cycle, it changes. So we will need to study that in more detail in the future. Another example of binary CI Camelopardalis, which gave a major outburst in the year 1998. Its binarity can only be confirmed by this little helium-2 lines, which moves back and forth with a pretty big amplitude, but it's very faint, and only high-resolution spectra with high signal-to-noise allow to measure the position of that line. It is shown here. The period is just 19 days, and the secondary companion is probably similar to what we found in the case of third Papis. It's not a black hole, it's not a neutron star, as was suggested earlier, but it's probably a subdwarf stripped core of a more massive star. Here is another one where we detected radial velocity variations, periods about 29, about 30 days. And here we can detect actually lines of the secondary cooler component. By the way, the Gaia distance of this star is very different. It's 3 times closer than what we can infer from the spectroscopic and photometric analysis of this star. So let's be careful with those measurements. And we also restored the evolutionary history of this star, but it may need to be refined in the future. Then this one is a very interesting one. It has a supergiant spectrum, but with some unusual lines in the spectrum of normal supergiants like neon one, more nitrogen lines, more aluminum lines, and silicon lines. When we did a radial velocity study, we found that it has a period of 130 days, and the mass function is so large that we suspected that the secondary component is a black hole. But there is an additional scenario, but I think it was introduced at an early seminar last year by Karim El-Badri. We probably need still to join forces to find another solution for this system. So here is a model of the those B-brackety stars of F Canis Majoris type. So the central part may remind the BE star, but there is also a ring of material with circumstellar dust. And here is the Herman-Russell diagram, the most recent version of it, with the position of primary components, mainly the black dots, and those which are parts of binary systems with both primary and secondary components. So bottom line that in this group, we can catch the process at different stages when the secondary companion is still transferring mass or it finished transferring masses. And as a result, the secondary companions like this one with the B, this one, or this one are located, or this one are located at different places in the Herman-Russell diagram. So this is another group of most likely all binary systems, which are simply closer probably at birth and undergo a more efficient mass transfer. And if we summarize results on both stars with both phenomena, then we can, this time, we can use even small telescopes to keep observing them, trying to reveal binarity of more objects. We just need relatively high resolution, I should say medium and high resolution. The higher, the better, of course, in order to catch the disk properties and the orbital motion. But observations need to be taken as frequently as possible. Also, we showed that the V over R variation method can successfully complement the methods of detecting binarity. And then finally, I would like to inform you that next year, our group is organizing an international conference on hot stars called Hot Stars with Life in Circumstellar Matter. Basically, this is the active B stars, but we include also young stars, protoplanetary nebulae, symbiotic stars, any object which contains a hot star with the circumstellar envelope. So here is the website of the conference. I know if it's gonna show up or not, but I invite you to take a look. And we started to contact possible invited speakers, and some of those who are here today may expect an invitation to give a talk at this conference. It's going to be in the end of October 2024 in the city of Almaty, Kazakhstan, which and the National University will host this conference. And I invite you to come there in person to see this beautiful city and high mountains around it. Thank you for your attention. I'm done. Questions?
Yes, indeed. Thanks a lot, Anatoly. So yes, do we have any question to Anatoly? So let me see. Not even
All right.
Dietrich has a question. Wow.
Okay, so did I put you asleep?
No, you do have
Yeah.
many people. A few ones had problem connection or had to go back, like Carol. So yeah, we missed a few ones, but yeah. Okay, not any question.
Yeah, there is a
B
hand
bracket
from
E on
Renee.
BE.
Yeah,
Okay,
I
then
had a question, but I couldn't find a hand on my screen.
Okay, René, go ahead. Go ahead.
Hi, Anatoly. This is René
Mhm.
I was just wondering, you showed the HR diagram of the B bracket E stars, and I was just wondering how many B bracket E supergiants we have in the galaxy nowadays compared to in the LMC.
Well, as far as I know, there are about 2,000 such objects. I'm trying to go through recent catalogs of optical and infrared photometry in order to find more objects to that. And mostly I'm revealing kind of FS Canis majoris objects, which are not supergiants. But we still need to study our recent spectra. There are many of them. There are about 15 new more candidates, but I just didn't have time to study them more closely. So we're doing that. But I'm not sure that we're going to be revealing more supergiants. As a matter of fact, we are sort of reclassifying those supergiants. For example, third Puppis is a supergiant spectroscopically, but in terms of mass, it's on the lower end of normal supergiants. So probably some definitions may be adjusted for these kinds of group.
Okie dokie. Thank you.
Thanks, René. Any other questions?
There, okay.
Okay.
So there is a question. Questions in the chat.
Yeah, saying, is it possible to study these stars? But I don't know which stars are you talking about, Eugene. Do you mean the BE, the B bracket E? So definitely, it's possible to study those stars at different wavelengths, of course, and with many different. Okay, it's both of them.
Yeah, okay, of course we can study them, but what do you mean? We are studying them and pretty actively. Active studies of active stars.
Definitely,
Okay.
yeah. We can do spectroscopy. We can do also, of course, in the optical photometry, and then there is infrared where you can do spectroscopy, photometry, a lot of things too, and you can do X-rays, and a little bit of UV also could be interesting. So there are a lot of things that we can do, Eugène. Depends on exactly what you want to do, but I think Anatoly has a point when saying, you know, that you need very long time. It's not sufficient to follow the star for a few months or a few days. Really having lots and lots of observation on the long term is really the key for. I mean, you can really see what's going on, and sometimes they do surprise us, right? A lot.
Yeah. Absolutely.
Yeah.
Mhm.
I had a question for you, Anatoly, if I may. Okay, I go back to Eugène after. I just asked my question first. So yeah, my question was, you have shown evolutionary tracks for one of those B bracket E, but for the other ones where you have the companion, did you also try to fit by evolutionary tracks?
Yeah, I actually showed two of them.
Okay.
First was that Fairy Puppies, the other one was MWC 728. We did another object, MWC 645, but it was we didn't find a good match because the published grids of such models are not very detailed. So we need to calculate more models. That's what we started doing that with the Mesa code and some other evolutionary codes. So hopefully, in maybe next year, even before that, our conference, we will get more results of that. And did I answer that?
Yeah, sure. Thanks.
And then
So-
if I go back to that question, the last question, chat astroseismology, basically you just reveal different time scales, which are probably connected to non-radial pulsations more than to longer time processes like formation of the disk, dissipation of the disk, and changes of the density distribution. And so astroseismology definitely fine, and it was shown by Dietrich, for example, and his team in the results from space missions on the bright B stars. Absolutely.
Hello. So I may complement that, saying that indeed it's also interesting to have this asteroseismology not only for a few days, but for a longer stretch of time, and see how it changes with the disk state, indeed. And Eugène was asking about the possible observatories. Well, for the moment, of course, people use a lot TESS because you do have high cadence for at least a month. Then we have a question by a newcomer called Jasir.
Yeah.
So he's asking, could it be possible that the B bracket R are evolved BE stars that reduce their rotation due to momentum transfer to the disk? The forbidden lines may be due to planet absorbed by the disk.
Well, at this time, for me, it's hard to imagine that planets would result in such strong spectral lines. It looks like, and that's what we are finding studying those stars, that the forbidden line emission comes from the outer parts of larger disks, and still we do discover secondary stellar components. It doesn't mean that the planets may not exist here. They may, but can we see the effects of those planets? I'm not sure yet. And I think the recording is going to be accessible, and
it will be on YouTube. It will be on YouTube indeed.
Yeah,
in a few days. So just wait, probably
yeah.
after Christmas, of course, because of the season. But usually after a few days.
And I also shared my PowerPoint presentation. So if anybody interested, so you can get it from me or Yale or Alex.
Thank you.
And there is what forbidden lines.
Any other questions?
Yeah. could it be possible that B bracketed stars are evolved B stars? Probably not, because B stars, quite a number of B stars, already have stripped cores, very hot secondary companions, just like some B bracketed stars. Probably, again, sort of a wild guess, based on the lower number statistics, that initially binary systems which become along the course of the evolution BE and B bracketed stars had different conditions in the beginning, different mass ratios, different orbital periods, and we catch them at least different times of the evolution. Yeah.
Okay. We have a reference also provided by Doug about one image, a resolved image of the disk around FSTMF. Any other remark or question to Anatoly? We went slightly over so 1 hour time, but if anyone has a last question.
By the way, Doug, thank you for the reference. I'm aware of it. There was somebody who studied FS kinetics for Joris with me, but for different reasons, this study has been delayed. But yeah, I'm watching everything. And anyway, any references, I'm grateful for any references. Thank you.
Okay, well, let me thank you again, Anatoly. Thanks a lot. And for everybody, Merry Christmas, Happy New Year already, and see you to the next meeting, of course, end of January, like always. Thanks a lot. Bye-bye, everybody.
Dietrich has something to say.
Dietrich wanted to clap.
Okay. Thank you. Thank you for.
Thanks very much, Anatoly.
Thank you for attending. I will be watching other seminars because it turns out that they're very interesting to me.
Okay. Thanks a lot.
Okay.
Bye-bye, everybody.
Bye. Bye.